everyone. Thank you all for being here. Today I'm going to be presenting on behalf of our colleagues, or my colleagues at the Colorado School of Mines in the Bologna group, which is Connor Murray and Dr. Bologna. So before we get started, a little bit about a background about what we do at Mines in this group. Essentially, Colorado is in this precarious position where water supply is diminishing, water quality in groundwater is also diminishing, and so our group focuses on turning ex situ processes into applications for drinking water treatment with the potential for someday it being applicable to direct potable reuse or indirect potable reuse. But specifically today, we're going to be talking about PFAS removal by FLUORO-SORB during laboratory scale experiments, because these are the emerging contaminants that are also important in all the other applications that we look for at Mines. So today is the story about PFAS and what we do. The outline, how to explain what we're going to do. Well, first, we're going to look at the background and the PFAS work we do at Mines, some engineering considerations because we need to know how to design these systems, a preliminary, and I emphasize preliminary, some of the data came out a few days ago, FLUORO-SORB PFAS removal performance, as well as the characteristics, and then introducing a decision support tool that will hopefully be available at some point in the future. So, if this was the map of the PFAS contamination in the US, we wouldn't be here. Unfortunately, it looks something more like that, where this is pulled from the Environmental Working Group and a group that studies PFAS and public health at Northeastern University. Those red dots are deemed highly contaminated sites, and the blue dots are the occurrences in drinking water or public drinking water supply systems. Also to note in that first slide, Canada is not exempt from these issues, although the Northeastern study, that was outside their scope. So how do we get exposed to PFAS? Out of a show of hands, how many of you think you have PFAS in your blood? Okay, we have a pretty well-informed audience. The true number is about approximately 97% of Americans, and that can come through manufacturing, through goods we inhale, ingest. It can come through landfill leachate, which can end up in biosolids. We eventually eat that. But most importantly, we want to look at groundwater, surface water, that are basically a direct exposure mechanisms. As you're drinking this water, you're being exposed, and in a lot of cases, accumulating in your system. So a little bit of background. Dr. Christopher Higgins is a professor at Mines currently. He started this PFAS work in the early 2000s at Stanford. He's really the pioneer of PFAS. He focused on analytical techniques and their fate and transport, as well as human exposure, which is really important work now. In the 2000s, people kind of ignored it. He's currently involved in approximately 15 PFAS projects, so he has a very, very heavy workload. That workload has led us to have a lot of analytical capabilities at Mines, such as multiple LC-MS systems, involvement in standardized PFAS method development, working with researchers and manufacturers on both targeted and non-targeted analysis of PFAS. Because the more you learn about PFAS, the less you know about PFAS. So, what we do analytically, we have targeted analysis, suspect screening, as well as looking for co-contaminants and general water quality. Today I'm going to be focusing on the targeted PFAS analysis, which is essentially a modified EPA method 537, because our systems were essentially, the methods were developed prior to the EPA coming out with this method. We used large volume injection as well as a QTOF. So CSM is in a pretty unique situation where we have a lot of pilot scale laboratories on campus and off campus. The top left picture is a new facility we're involved with in East Denver, which is essentially, it used to be a produced water treatment facility for an oil and gas company. So there's every sort of technology there and available to us to look at different treatment technologies. We, in the bottom right, have a full-scale wastewater treatment facility on campus that treats the dorm rooms' wastewater. And we have a pretty good ability to build pilot-scale treatment systems in-house, such as the bottom left corner. So a little bit of background. I might be the only person presenting today that is at liberty to say where some of these issues are, because it has been so widely published, such as this article in the New York Times, which essentially is accusing the U.S. Air Force of contaminating drinking water from a site in Colorado Springs, and the plume migrating all the way down to Fountain, Colorado, which uses groundwater as their supply. And so this is a CDPHE map that's public of all the contamination and the plume in the wide field aquifer, which prior to these issues being published was their only supply. So that led to mines being in a pretty fortunate position. You have this huge site very close to home, and you have these analytical capabilities and essentially experts in the field. So who is the Air Force going to call? Well, they're going to call their legal team, they're going to call their PR, and then they call mines to set up a system and see what they can do. So this is the first pilot study on the left, is essentially 4 different GAC contactors evaluating the efficiency of all the different media. That led to more studies, and on the right is a preliminary study of submicron powder activated carbon with ceramic microfiltration. That's going to be also a study moving forward with Arcadis as one of the industry partners. The left study is currently being rerun with 3 ion exchange products as well as a GAC replicate to confirm the results from the previous study. And these studies last around 7 months, so the data isn't there from the day to the next. We also look at novel treatment technologies. This is nanofiltration and concentrate treatment. I won't get into that too much because it was run by another one of our lab members, Charlie Liu. His email's there if you'd like to contact him. Essentially, it's showing that we can get up to 95% or above 95% rejection of these compounds. And that means when you're rejecting all these compounds, they're all going to be accumulating in the concentrate stream. And you have to figure out what you're going to do with that heavily contaminated concentrate stream. One of the ways they've thought is UV bisulfite. I'm not very aware of all the processes that occur in that situation, but it has effectively been demonstrated to work, and this is going to be published very soon if it hasn't already been published. So for the engineers in the room, how do we design these systems? First, one of the most important components is the empty bed contact time of your vessel, because that's basically dictating how fast, slow things can sorb and desorb. Hopefully sorb in this case. You don't want things coming back out into your drinking water. The guidelines for the AWWA say that the median for empty bed contact time is approximately 10 minutes. However, the CDPHE has come out with recommendations. I'm going to reference the CDPHE a little bit, Colorado Department of Public Health and Environment, because we're working in Colorado generally, of 10 to 20 minutes with hydraulic loading rates of 2.5 gallons per minute per foot squared and some sort of lead lag configuration, which means you have a lead column and a lag column. The ion exchange systems somewhat differently, shorter empty bed contact times, which means similar hydraulic loading rates, but bed depths are different. And so what I mean by lead lag is essentially you can have 2 contactors. The contaminated water can flow into the first one. It then flows into the second one. They can be set up to have either 10 minutes empty bed contact time each, which would get you to 20, or 5 and 5. Ideally 10 and 10 just for safety. Then you have your drinking water at the other end. When that first column is going to get exhausted much faster than the second column, you could replace the first column, reverse the direction of flow, and that way it becomes the second column. And now you exhaust your second column and can replace and so forth. There are a lot of ways to do this, including more parallel, more in series. It's really dependent on your source water, what you're trying to do with the water. But there are some guidelines out there for how to design these systems. So this is an example design of the site we were previously referencing. It has a lead lag system. That complex piping network in the middle is what I'm referring to when it can go interchangeably from one to the other. They're currently using Calgon F400 with a loading rate of 3.8 gallons per minute per foot squared, a very high empty bed contact time, because this was a little bit of a knee-jerk reaction to the situation, and they deployed a system that was a little bit over-designed, but with the keeping in mind that this was designed for people safety. So comparing adsorbents. What are the advantages of GAC? What are the disadvantages? GAC advantages, when we're talking about relative, it's relatively cheap. There's non-selective adsorption, so you're going to remove a lot of organic carbons. There's high surface area per mass. Unfortunately, it has very slow adsorption kinetics, and you can have quick breakthrough of short compounds. And the PFAS breakthrough is very dependent on the GAC itself. One GAC to another GAC are going to be completely different, so you need a lot of pilot scale testing. Ion exchange advantages. It has faster adsorptions, which can be shown by the shorter empty bed contact times, slower breakthrough for most PFAS, but not all PFAS, and you have the potential to regenerate on site. That's also possible for GAC, but a lot less likely. The disadvantages are that relatively more expensive. Certain PFAS species have lower adsorbability because a lot of these media are anion exchange, and so that means, as Jin perfectly mentioned, there are a lot of cationic, neutral, a lot we don't know, and so all those are going to be moving through because all you're doing is taking the negative charge and replacing it with a chloride. Breakthrough of short chain PFAS has still a little bit problematic, maybe a little bit less so, however. And that, as I mentioned, adsorption capacity is strongly impacted by anions, which is not something that we have studied in depth, but say a sulfate, a chloride, high concentrations, there might be a lot of competition for those sites. So that brings me here today. Development of absorbent material that's cheaper, relatively, with better PFAS adsorption would be extremely beneficial. So PFAS work at mines. We have the pilot scale evaluation of a lot of adsorbents, the NFRO with UV reductive concentrate treatment, submicron powder activated with ceramic microfiltration, a lot of short chain PFAS projects, the sustainability of IX regeneration, and FLUORO-SORB adsorbents. So for this site, this is a site map of a different Air Force base, essentially where we got the water to run these experiments. It's important to note the high concentration at the monitoring well, which is where the water was pulled from. The FLUORO-SORB experiments. So we received 350-gallon totes of contaminated groundwater. We analyzed for PFAS types and their concentrations, also looked at the background water matrices. Essentially, what I'm trying to highlight in this table are your carboxylates and your sulfonates, generally the ones that the EPA or other regulatory agencies have been looking at to regulate. We're not looking at the suspect screening as of right now. However, that could be in the future. So TOC has been shown to be very important in terms of removal in these column systems. It was 3.3 plus or minus 0.5. The pH was relatively neutral. Calcium, magnesium, sodium, potassium, sulfate, all listed on there. That was based on a very preliminary data analysis on done a few weeks ago. So it could have changed from experiment to experiment. We haven't received the results from this past week. So the idea of the setup is that we have this contaminated water. It's going to be pumped into columns. You're going to have some head over each column media so that you can have hydrostatic pressure being dictating how much you're letting through. You're sampling at the influent, you're sampling at the effluent, and the idea was to have it go through the second column segment in series. However, because we never saw breakthrough as of right now, I'm going to be focusing on that first chunk. The column itself is 1-inch diameter with FLUORO-SORB 200 in parallel to and in series with GAC and ion exchange resin. As I mentioned, really we're only focusing on FLUORO-SORB 200, GAC F400, FLUORO-SORB, and FLUORO-SORB. But in the future, we will have results for those bottom columns. So it's a 1 foot with bed height depending on the empty bed contact time, which is a little bit more difficult than it seems because your flow rate can change minorly. That affects your empty bed contact time, as well as compaction of media. That can change your empty bed contact time. But the total empty bed contact time as an average, granular activated carbon, approximately 10 minutes, ion exchange, approximately 5, and FLUORO-SORB approximately 10 minutes, with a hydraulic loading rate of about 0.6 GPM per foot squared. That's a little low relative to the CDPHE guidelines. However, that's just a function of the fact that there's not very much surface area that we're working with in our columns. So then the results. We're looking at PFOS removal here. It had a very high influent value of 25.3 micrograms per liter. To keep in mind, the concentration over the concentration initial of 0.003 is what the 70 nanograms per liter limit would be if that were enforceable. So that's the top line. That's this top line. And what we see is as bed volumes get treated, there's relatively low concentrations coming through the column. And then later in the experiment, it seems like GAC is starting to break through. You might have a question about, well, why wasn't FLUORO-SORB tested at these bed volumes? That is just a fact of everything is normalized to the volume of the bed. So this data point out here for GAC is the same sampling time as this data point for FLUORO-SORB. However, because the bed volumes were slightly different, essentially the time to get to the certain amount of bed volume will be different as well. So each volume processed as of the last sample was approximately 420 liters per column segment. So what does that mean in terms of micrograms of PFOS per gram of media? That's really important. That's how a lot of studies report their findings in drinking water treatment facilities. We're seeing a very high removal per gram of media compared to previous studies, but that may be a function of the fact that the influent concentrations are higher, but a little bit more research is required with that in mind. We're also going to look at PFOA removal, and we also see this trend that is consistent with PFOA, where GAC seems to be breaking through. It's also important to note that effluent concentrations were higher than expected near that start of the experiment. More samples would be required to understand that occurrence. It could also be analytical difficulties or something along the lines, because the instrumentation isn't perfect, methods aren't perfect. So if another experiment were to show that again, then that would be a little bit more concerning. But as of right now, we're kind of going to sidestep that. So what that means in terms of micrograms per gram of media, between 30 and 50, and this research is still ongoing, so hopefully in the next week or two we're going to have better data. But it's important to note that in both of those graphs so far, we haven't gotten to 70 parts per trillion. So previous studies have reported lower microgram per gram values, but the higher bed volumes treated versus the bed volumes treated is really it's a little bit of a subjective study in terms of what you're publishing. So you have to be careful when you're looking apples to apples. Different water matrices are going to have different removal. These parameters are a function of the experiment setup, the column dimensions, the empty bed contact time, co-contaminants, and the competition for the adsorption sites, as well as chain length, which is what we're going to talk about next. So this is a sulfonates removal, essentially anything that has with an S. The important ones in the regulation world right now are PFOS, PFHXS, PFBS. And here at the top three colors, the top three, we can see there are a little bit of discrepancies. Some, we believe, outlier points or short chain breakthrough. But as of right now, that's uncertainty. But in general, when you dive into each contaminant individually, you see that granular activated carbon seems to not be working as well as FLUORO-SORB. And that can be essentially seen in most of the other graphs as well. So there's reference points there for what concentrations that actually means. Important to note that the influent concentration is fairly high for a drinking water source, but it's not unseen. So when we're talking about regulation, states that are moving to regulation here is a lot different than states in the 50 to 70 range in terms of when you need to replace your media. So we did a similar analysis for the carboxylic removal. That's PFPEA, PFHXA, PFHPA, PFOA, essentially the chain length 5, 6, 7, 8. So here we can clearly see that your F400, those top four, so blue, orange, gray, and yellow, are seeing breakthrough much earlier than all the others. Once again, we're going to need to continue. It's preliminary data. Continue to extend that line out for the FLUORO-SORB to see how it compares at later times. But right now, this is very positive data to be looking at. So diving into all the specific contaminants, we look at the PFOA. This is the 50 nanograms per liter, the 10 nanograms per liter. And so in a regulatory standpoint, if these data points happened at a certified laboratory that you were sending your data to, the EPA would probably have an issue with that if that was regulation. However, after a certain amount of time, it dropped back down. So we're fairly confident that these are outliers. However, it can't be determined without further sampling. And so essentially, all the trends seem to be about the same, where granular activated carbon is seeing breakthrough earlier than FLUORO-SORB. But as I've mentioned several times, research, we need to continue and also repeat the experiment because one time is not enough to make conclusive decisions. But this is very positive.
I have a question.
Yeah.
So when you did your column study, you use an individual pump for each column.
Correct. So the question is if I use a pump for each column.
Yeah.
Okay, so we got around needing 4 peristaltic pumps by using one pump, having it feed to a top column. And I think there's going to be another picture later that shows it a little bit more clearly. But basically, pumping it to a tank, that tank would be elevated, so it had hydrostatic pressure above the columns. And that way, it could feed by gravity downwards. The issue we saw with using a pump is that had it been 4 different pumps, you would need to calibrate the pumps. They would need to be calibrated exactly the same way. And from cartridge to cartridge on the same pump, you would also have issues like that. So we saw the easiest way to get around that was pumping it above and letting it gravity feed, because we've seen a lot of these systems are gravity fed in terms of granular activated carbon contactors. And it's also, I should probably also mention that there were valves at the bottom, so as well as flow meters, so that's how we controlled how much water was actually moving through the columns.
So the flow rate is similar?
It's correct. So we can control the flow rate on each of them, and that way you can control the flow rate based on the volume and based on the time that you're trying to have a droplet of water spend in that column. So the question is the bed volume for the FLUORO-SORB and the flow is less, is that what you said? So the bed volume for the FLUORO-SORB is slightly greater than the granular activated carbon, but because that bed volume is bigger and the flow rates were similar through it, it means it's seen less bed volumes. However, it's seen the same volume processed, if that makes sense. Okay. So moving on, we have the FLUORO-SORB characteristics, because that's also important when we're looking at designing systems. We essentially did a permeability test, a 4-inch diameter column, 2 feet of media, and compared the head above the media to what the surface loading rate would be. This was done at 17 degrees C. Any technical data sheet is going to have this at different temperatures, but we are a little bit time limited, so that is the next step in this part of the study. And how that looks in terms of superficial velocity, which is the surface loading rate, the hydraulic loading rate, and the pressure drop in inches of water per foot of bed, that's how engineers would look at it and say, if we need a contactor that has 2 feet of media, how how much hydrostatic pressure above that media are we going to need to get the hydraulic loading rate that we're looking for. So you would look this up in the technical data sheet, and you would go basically across, figure out how much feet of bed you need. That would determine how many inches of water, and then move across, and then you would link those two together. So this was the bed expansion. It was done in backwash mode. A lot of these systems are not going to necessarily need backwashing because you're going to be replacing the media when it gets exhausted. However, it's important to note that the bed expansion was slightly greater than GAC, which was approximately 45 to 50% at the loading rates there, shown there, which essentially means that if you are going to be backwashing, you need to over-design your tanks slightly more because you don't want to be flushing that media backwards out of the tank. So past, current, and future PFAS studies. Basically, we've been looking at all these different technologies with the goal of creating a database so that whether it's the Department of Defense, whether it's the EPA, whether it's consultants, they can know what's best for their clients, what's best for their own sites, what would be the most cost effective, what's sustainable. And so what we do is we create a decision support tool. Ideally, you put in your influent water characteristics, you put in the removal technologies you want to compare. You can either use literature values for the removal capacity, or you can enter your own that have been tested in pilot studies, and then any other capital and operational costs. And that is basically just going to generate a life cycle cost assessment over time of what you should expect. So the preliminary cost assessment, operational parameters are going to be different because of the pressure drop and bed expansion are slightly different. But overall, life cycle costs are driven by media replacement. And if it continues the way the previous graphs have shown, there would be less media replacements required if you had more micrograms of contaminant removed per gram of media. But complete cost assessment is required because all of this is site-specific. All of this is the background matrix water specific. So some food for thought, just a little bit of a conclusion. Water quality policies, they don't have a very good reputation. It was studied as recently as 2019, where the benefit-cost ratio of these quality policies was found to be 0.37. That means the bar is very, very low when you're looking at the cost benefit of a policy. However, the EPA is still going to look at this and want to see more benefit than cost associated with it. So the benefits of reducing PFOA, PFOS, and others is that there are hundreds of millions of dollars spent on healthcare costs that could be attributed to PFAS. We know they interact with our body. However, the adverse effects are a little bit less studied because it's hard to prove causation is not correlation, correlation is not causation. So more research is required. When we think about costs, these processes could all be very expensive. So it's also important to note that the EPA is looking at CERCLA as a possible way to deal with these contaminants. If they deem them hazardous contaminants, that relieves a lot of pressure on water utilities, and they can pass off the cost to the people they think are responsible if it's proven that they are responsible. So research is ongoing. I hope I've made that fairly clear. It's a little bit too early to determine the full adsorption capacities of the media evaluated because we are essentially nowhere near the full adsorption capacity. The preliminary data is fairly favorable. It appears to be comparable with GAC in terms of removing the suite of contaminants we've looked at, and it seems to be a viable alternative, but additional sampling and analysis would definitely be required. So any questions pertaining to the previous studies can be directed to Dr. Bologna, and this is what it looks like when you finally get your column system running. So definitely going to acknowledge SETCO. Thank you for the funding, the support for this study, as well as all of the support team at the Colorado School of Mines, the Strathman and Higgins groups, which are very involved with all of our studies, as well as our industry partners. And that's all I have. With that, I'll take any questions. Yeah.
So what's the final empty bag contact time in your column study for FLUORO-SORB?
So the question is what the final empty bed contact time is for FLUORO-SORB?
Today is 10 for both, 10 minutes for both gas and FLUORO-SORB.
Correct. So it was approximately 10. However, we erred on the side of caution, so it's approximately, I would say 10 and a half is probably more the realistic total empty bed contact time for each FLUORO-SORB column.
10 half.
I would say it's approximately 10 and a half, yes.
For gas, it's also 10.
Yes, correct. Yes,
I'm assuming that the GAC you're using is all virgin GAC.
correct, yeah.
Any thoughts about how that might look if you were using regenerated gas?
I don't think I want to speculate on granular activated carbon given where I'm giving my presentation, but I'd be happy to talk to you about it later. Anything else? Question?
Did your bed volume change at all during the column testing? Like,
Slightly. So initially we had anticipated to be going upflow through the columns because that's what a lot of column studies in research seem to be reporting. However, there were a lot of unanticipated kind of air intrusion issues into the columns, and that really messes with the flow rate through the columns that's expected. So when we did change into downflow, there were a little bit of compaction on the granular activated carbon side. So when I said we designed for about 10, when it got saturated and compacted, it probably went from being what I said was like the 10 and a half down to about 10. And so there's a little bit of compaction on that side. And then because of the bed expansion on the initial startup, there's a little bit of uncertainty, but basically we measure the empty bed contact time and the bed volume through time because all it is the cross-sectional area times the depth of the media, so we can still get a pretty good idea of it through time.
was the media prepared prior to the column testing, or was it still like pretty fluffy when you started the test?
So this was kind of a point of uncertainty. However, we took the raw media, did not prepare it. As it was sold, it was put into the columns.
Okay. So that could actually explain your initial contamination coming through. Maybe, I don't know.
It could. However, it's pretty hard to speculate
Right.
on that.
Sure.
Okay.
Just a quick comment on that. So you were looking at the initial, a little bump, right? You were thinking that might be contamination of the sorbent. Is that what you're saying? Yeah. So you were thinking that could be contamination from the sorbent, or?
Just if the media was really fluffy in the
Yeah.
at the beginning of the test, we had basically less contact area of things with the
I-
input getting
If I can
Oh, I see.
interject
Just
a
kind
little
of
bit.
short. What's that kind of short flow? Okay.
If I can
Yes.
interject, I think what
Yeah,
he's
I
getting at is
misunderstood.
that because at the start of the experiment there were little peaks that were maybe unexplainable, there's potential sort of preferential path that started at the start of the experiment and would have worked itself out over time.
as the
It's a possibility.
acted.
Yeah.
And so did you soak your gas, all that, before you pack the column?
It was run with deionized water for several bed volumes, yeah.